The universe is filled with billions of stars, trillions of planets, and everything needed for life to exist. Yet after decades of searching, we have found nothing. No signals, no visitors, no evidence that anyone else has ever been here. And this strange silence is what scientists call the Fermi Paradox. In this video, we are going to follow the real scientific journey behind that mystery, from unexplained signals and powerful cosmic events to distant planets that might hold signs of life. And you will understand what we have actually discovered, why scientists expected to find evidence of other civilizations, and why that expectation keeps failing. Because this is not just a story about space. It is a story about a question that challenges everything we think we know about life in the universe, and by the end, you will see why the answer to this paradox may be far more important and far more unsettling than anyone expected. On a quiet night in August 1977, a machine listening to space heard something unusual. At Ohio State University, a radio telescope called Big Ear was scanning the sky. Its job was simple: listen to radio noise coming from space. Most of that noise is random, produced by stars and galaxies. But on August 15th, 1977, something different appeared. The signal came at a very specific frequency, 1,420 megahertz. Scientists had long believed that if intelligent life wanted to send a message, this is the frequency they would use. It is linked to hydrogen, the most common element in the universe. In simple terms, it is like a universal channel that any advanced civilization would know. What made the signal special was how clean it was. Natural signals are messy and spread out. This one was sharp and focused. It was also strong, about 30 times stronger than the usual background noise. It lasted for 72 seconds. That detail mattered. The telescope was slowly scanning the sky as Earth rotated. A signal lasting exactly 72 seconds suggested it came from a fixed point far away, not something random or nearby. A scientist named Jerry Ehrman noticed it while checking the data. He circled it and wrote one word beside it: "Wow." The name stayed. By the standards of science, the signal looked exactly like what an artificial transmission should look like. It matched predictions, it followed the rules, and then it vanished. Scientists looked again, and again, for years, then decades. It never came back. This created a serious problem. In science, one event is not enough. You need to see something more than once to prove it is real and understand what caused it. Without that, there are always other possibilities. It could have been a rare natural event, it could have been interference, or it could have been something much more important. But there was no way to test it again. So the wow signal became something strange, not proven, not dismissed, just unresolved. It raised a deeper question. If a real signal from another civilization appeared only once, would we even recognize it? Or would it disappear before we understood what we were seeing? In the years that followed, scientists built better instruments, more powerful telescopes, more sensitive detectors, and soon the universe would send something even harder to ignore. Not a steady signal, but a sudden, powerful burst. For nearly 30 years after the wow signal, the universe remained silent. No confirmed messages, no repeating patterns, just noise. And then, in 2007, something changed. At the Parkes Observatory in Australia, a scientist named Duncan Lorimer was reviewing old data from a radio telescope. Hidden inside the recordings was a signal that lasted less than a second. But in that brief moment, it released an enormous amount of energy. This was the first fast radio burst. Unlike the wow signal, which was steady and narrow, this was sudden and explosive. It appeared for just a few milliseconds and then vanished. But the energy it carried was extraordinary. In that tiny fraction of time, it released as much energy as our sun produces in an entire day. To understand how extreme that is, imagine compressing 24 hours of sunlight into a blink of an eye. At first, many scientists did not believe it. The signal was so unusual that the simplest explanation seemed more likely. It could be a glitch, instrument error, even interference from Earth. In fact, Similar signals were later traced to something as ordinary as a microwave oven being opened at the wrong moment, so the scientific community remained cautious. But then more signals appeared. Different telescopes, different locations, same pattern. Short, intense bursts coming from far beyond our galaxy. By the early 2010s, the number of detections had grown. By 2025, thousands of fast radio bursts had been recorded. This was no longer an anomaly. It was a new category of cosmic event. Researchers began tracing some of these bursts back to their sources. In 2020, a major breakthrough came when one fast radio burst was linked to a magnetar inside our own galaxy. A magnetar is a type of dead star, the collapsed core of a massive star with an extremely powerful magnetic field. When its structure shifts, it can release vast amounts of energy in an instant. This provided a natural explanation, at least for some of the bursts, but not all. Some fast radio bursts repeat in patterns that are still not fully understood. Their timing is irregular, sometimes clustered, sometimes silent for long periods. And this is where the question returns. Could all of them be natural, or are some of these signals something else? The idea remains controversial, but it is not ignored. Scientific programs like Breakthrough Listen have pointed powerful radio telescopes toward these sources, searching for anything unusual hidden within the bursts. So far, no clear sign of artificial origin has been found, but the uncertainty remains, because these signals are not weak, they are not rare. They are happening across the universe, in numbers that suggest something fundamental is at work. The stakes are different now. We are no longer asking if strange signals exist. We are asking what is powerful enough to create them, and whether all of them can truly be explained. Because the next discovery would not come from a signal at all. It would come from a star that refused to behave. In 2015, a distant star began behaving in a way no one could explain. It did not explode. It did not fade slowly. It flickered. Deep within data collected by NASA's Kepler Space Telescope, a citizen scientist named Tabitha Boyajian noticed something strange. The star, catalogued as KIC 84-62852, was dimming, but not in any way astronomers had seen before. Normally, when a planet passes in front of a star, it blocks a small, predictable amount of light. Even a massive planet like Jupiter blocks only about 1% of its star's brightness. This star was dimming by up to 22%. That is not a planet. Even more puzzling, the dips were irregular. They did not repeat on a fixed schedule. Sometimes the brightness dropped slightly. Other times it plunged dramatically. The pattern had no clear rhythm. To understand why this was so unusual, imagine watching a light bulb from far away. If something passes in front of it, the shadow should be consistent and predictable. But here the light was being blocked by something uneven, shifting and changing over time. The discovery quickly drew attention across the scientific community. Astronomers began proposing explanations: clouds of dust, swarms of comets, debris from a recent collision. Each idea could explain part of the data, but none fit perfectly. Then came a more radical possibility. In 2015, astronomer Jason Wright at Pennsylvania State University suggested that the dimming pattern might be caused by something artificial, not a natural object, but a massive structure orbiting the star. The concept was known as a Dyson swarm, a collection of structures built to capture energy from a star. Not a solid shell, but a scattered network of large objects, each blocking a different amount of light as it passed. For a brief moment, the idea captured global attention, because if true, it would mean we were not just detecting life. We were detecting engineering. But science does not move forward on possibility alone. It tests. In 2018, researchers analyzed the star using multiple wavelengths of light. This allowed them to see not just how much light was blocked, but how different colors were affected. The result was decisive. Blue light was dimmed more than red light. That pattern is not produced by solid objects. It is a signature of fine dust particles which scatter shorter wavelengths more strongly. The conclusion was clear. The dimming was caused by dust, not a megastructure. The extraordinary explanation collapsed, but something important remained. For the first time, humanity had observed a signal strong enough to seriously consider the possibility of large-scale alien engineering, and had the tools to test it. The instruments worked, the method worked, the process worked, and that changed the search forever, because now we knew what to look for, and more importantly, we knew that the universe could still surprise us in ways that force even the most cautious science to ask extraordinary questions. But the next discovery would not be a signal, it would not be a burst, and it would not be a distant star. It would be something much closer, something that passed directly through our own solar system. In October 2017, something entered our solar system that did not belong here. It was not a comet, it was not an asteroid, and it was not bound to the Sun. At the Pan-STARRS 1 telescope in Hawaii, a survey system designed to detect near-Earth objects picked up a faint point of light moving unusually fast. At first, it looked like another small object passing through the inner solar system, but when astronomers calculated its path, the numbers did not make sense. The object was moving too fast to be held by the Sun's gravity. Its trajectory was hyperbolic. In simple terms, it was not orbiting our star. It was passing through. This was the first confirmed interstellar object ever detected. It was named Oumuamua, a Hawaiian word meaning messenger from afar. What made it remarkable was not just where it came from, but how it behaved. Observations suggested it was highly elongated, possibly 10 times longer than it was wide. It tumbled through space in a chaotic motion, and as it passed close to the Sun, something unexpected happened. It accelerated, not dramatically, but enough to be measured, enough that gravity alone could not explain it. For comets, this is normal. As ice heats up, it releases gas that pushes the object like a jet. But Oumuamua showed no visible gas, no tail, no coma. It looked like a rock, but it moved like a comet. Scientists proposed explanations: invisible hydrogen outgassing, nitrogen ice sublimation. Each idea could account for the acceleration without producing a visible tail, but none could be confirmed directly. And then came a more controversial suggestion. In 2018, Harvard astrophysicist Avi Loeb proposed that Oumuamua might be artificial. A thin, light structure pushed by radiation pressure from sunlight. Something like a light sail. The idea was not widely accepted. Not because it was impossible, but because natural explanations existed. In science, the simplest explanation is preferred until proven otherwise. And then, just as quickly as it arrived, Oumuamua was gone. We had only a few weeks to observe it before it disappeared into the outer solar system beyond reach. No second chance, no close-up images, only data collected in passing. 2 years later, in 2019, a second interstellar object appeared. Discovered by amateur astronomer Gennady Borisov, this one behaved exactly as expected. It was a comet, complete with a visible tail and gas emissions. Familiar, predictable, natural. Then in 2025, a third object was detected by the Atlas survey in Chile. This one was larger, possibly several kilometers across. Its path took it close to multiple planets. And for a critical period during its closest approach to the Sun, it was hidden behind the Sun itself. For weeks, we could not observe it. The alignment was unusual. Statistically unlikely, but not impossible. Once again, the question surfaced. Could it be artificial? To test this, scientists used the Green Bank telescope in the United States to scan for radio signals, sensitive enough to detect emissions as weak as a mobile phone. They found nothing. No signals, no transmissions, no evidence of technology. All three objects, different in appearance and behavior, shared one conclusion. They were natural, but their existence revealed something deeper. These were not rare events. Astronomers now estimate that thousands of such objects may pass through our solar system at any given time, unseen. Fragments of distant worlds, drifting silently between stars. The space between star systems is not empty, it is filled with debris. And now, for the first time, we are beginning to see it. This changes the scale of the problem, because if material can travel between stars, then so could something else. The question is no longer whether objects can reach us, it is whether anything ever chooses to. And the next clue would not come from objects or signals, it would come from chemistry, from the faint signature of something that might be alive. In 2023, for the first time in human history, scientists detected the chemical ingredients of life on a distant world. Not on Mars, not on a moon in our solar system, but on a planet 124 light-years away. The planet is called K2-18b. Using the James Webb Space Telescope, one of the most advanced scientific instruments ever built, a team led by astronomer Nikku Madhusudhan at the University of Cambridge studied the light passing through the planet's atmosphere. This method is simple in concept. When a planet moves in front of its star, a tiny fraction of starlight passes through its atmosphere before reaching us. Different molecules absorb different colors of light. By studying those changes, scientists can identify what gases are present. It is like reading a chemical fingerprint from across space. What they found was already significant: methane, carbon dioxide. These are carbon-based molecules. On Earth, they are closely linked to biological and geological processes. Their presence does not prove life, but it shows that the basic chemistry needed for life exists. K2-18b itself is unusual. It is about 8 times more massive than Earth and likely covered by a vast global ocean beneath a thick, hydrogen-rich atmosphere. Scientists call this type of world a Hycean planet, a place where liquid water could exist, but under conditions very different from Earth. Then, hidden in the data, there was something else, a faint signal, dimethyl sulfide. On Earth, this molecule is produced almost entirely by living organisms, especially microscopic marine life. It is part of the chemical cycle of oceans. In simple terms, it is a possible sign of biology. But the signal was weak. In 2023, it reached only about a 2 sigma level of confidence. That means there was still about a 5% chance it was just random noise in the data. That is not enough to claim a discovery. So scientists looked again. In 2025, using a different instrument on the James Webb Space Telescope, the signal appeared stronger. The confidence rose to about 3 sigma. The chance of it being random dropped to around 0.3%. This was the strongest hint of life ever detected beyond our solar system. But still, it was not enough. In science, the standard for confirmation is 5 sigma, a level so strong that the probability of error becomes almost zero. And then came the challenge. Independent teams reanalyzed the same data. They found that the signal depended heavily on how the data was processed. Small changes in assumptions caused the signal to weaken or disappear entirely. There was another complication. In 2024, dimethyl sulfide was detected on a comet in our own solar system, a place with no life. This changed everything. If the same molecule can be produced without biology, then it is no longer a clear sign of life. The interpretation became uncertain. Some scientists argued the signal was real but unexplained. Others argued it was an artifact of noise. The result was not a discovery, it was a debate. And that debate revealed something deeper. For the first time, humanity was not just asking if life exists elsewhere. We were analyzing real data from a real planet and arguing over possible evidence. This is a new stage in science, but it also exposes a limitation. Even with the most powerful telescope ever built, we are working at the edge of what we can detect. Signals are faint, uncertainty is high, and conclusions are fragile. If life exists on distant worlds, it may not announce itself clearly. It may appear only as a weak signal, buried in noise difficult to confirm. And if that is the case, then the silence we observe may not mean absence. It may mean we are not yet able to see clearly enough. Because before we can answer whether life is common, we must understand how difficult it is to prove it exists at all, and that realization leads to a much larger problem, not of detection, but of scale. By 2018, scientists reached a troubling conclusion. We had not failed to find extraterrestrial signals. We had barely looked. A research team at Pennsylvania State University attempted to measure how much of the search for intelligent life had actually been completed. Their approach was simple in concept, but unsettling in result. They compared the total possible search space to what we had observed so far. This search space is not just about distance. It includes every direction in the sky, every radio frequency, every signal type, and every moment in time. a vast combination of possibilities. To make this understandable, they used an analogy. Imagine all the water in Earth's oceans. Now imagine taking a single hot tub of water from that ocean and examining it carefully. That is the equivalent of everything humanity has searched so far. A hot tub compared to an ocean. This is the scale of the problem. The Milky Way galaxy alone contains between 200 and 400 billion stars. Many of those stars have planets. Current estimates suggest there may be more planets than stars, possibly over 1 trillion. Among them, billions may exist in regions where liquid water could form. Places where life, at least in theory, could exist. And yet, our search has covered only a tiny fraction of this vast system. Most SETI programs focus on narrow ranges of radio frequencies, especially around the hydrogen line at 1420 MHz. This is considered a logical channel for communication, but this assumption is based on human reasoning. We are searching where we think signals should be, not necessarily where they are. If a civilization uses a different method, optical lasers, neutrinos, or technologies we do not yet understand, we would not detect it. There's also the problem of time. Signals travel at the speed of light. If a civilization sent a message from 1,000 light-years away, it would take 1,000 years to reach us. If they transmitted it 900 years ago, it has not arrived yet. If they transmitted it 2,000 years ago, it passed Earth long before we had the technology to detect it. The window in which a signal exists and we are capable of receiving it may be extremely small. This creates a situation where even if signals are common, detection remains unlikely. Modern programs like the Breakthrough Listen initiative have improved the search. Using powerful telescopes, scientists are scanning thousands of nearby stars with greater sensitivity than ever before. But even this is limited. Thousands of stars out of hundreds of billions. We are sampling the galaxy, not surveying it. And yet, despite this limitation, something begins to stand out. As instruments improve, as coverage expands, one result remains consistent. No confirmed signals, no verified transmissions, no evidence of technological activity. At some point, the absence of evidence begins to feel significant, not as proof, but as pressure. Because the numbers suggest something should be there, the scale suggests something should have happened, and yet we see nothing. This is where the question begins to change. It is no longer just about how we search. It becomes about what we expect to find. Because if the universe is this vast and this old, then even rare events should have left traces, and that leads to a deeper problem, not of observation, but of contradiction, a contradiction that would be first spoken decades earlier, in a simple question asked over lunch. In the summer of 1950, a simple question changed the course of scientific thinking, and it did not come from a laboratory experiment or a telescope, but from a conversation over lunch. At Los Alamos National Laboratory, physicist Enrico Fermi was sitting with colleagues discussing the possibility of extraterrestrial life, and while the conversation was casual and speculative, Fermi suddenly asked a question that carried far more weight than it seemed. Where is everybody? Behind that question was not curiosity alone, but calculation. Fermi was combining what was already known about the universe into a single line of reasoning. The Milky Way contains hundreds of billions of stars, many of them far older than our Sun, and observations now confirm that planets are common around those stars, while the basic ingredients for life, such as carbon, water, and energy, are widely available throughout the galaxy. Given enough time, even a very small probability of life developing should lead to many civilizations, and if even a fraction of those civilizations develop technology capable of leaving their home systems, then slow and steady expansion across the galaxy would be possible. This expansion would not require advanced or hypothetical physics. Even at modest speeds, far below the speed of light, a civilization could spread from one star system to the next, gradually building a network that would eventually reach across the entire galaxy. The timescale for this process is estimated to be a few million years, which may seem long from a human perspective, but becomes almost insignificant when compared to the age of the Milky Way, which is over 13 billion years. This means that such expansion could have happened many times over. Fermi's conclusion followed directly from this reasoning. If intelligent life is not extremely rare, then the galaxy should already contain clear evidence of it, whether in the form of signals, probes, or large-scale structures. And yet, when we observe the sky, we find none of these things. This is the contradiction at the heart of the problem. On one side, the numbers strongly suggest that we should not be alone, while on the other side, every observation we have made suggests that we are, and both of these conclusions cannot be true at the same time. To understand the scale of this contradiction, it helps to look at the timeline. Our Sun formed about 4.5 billion years ago, which means the galaxy had more than 8 billion years before Earth even existed to produce life elsewhere. If a civilization had emerged just 1% earlier in the galaxy's history, it would be more than 100 million years older than humanity, a difference so large that it is difficult to fully grasp. On Earth, 100 million years ago, dinosaurs still dominated the planet, and the gap between us and such a civilization would not simply be technological, but evolutionary. Despite this enormous head start, we detect no clear signals, no confirmed structures, and no evidence that any civilization has ever reached or influenced our region of space. The galaxy appears silent. This problem became known as the Fermi Paradox, not because it lacks possible explanations, but because it presents a direct conflict between what we expect to see and what we actually observe. Either intelligent life is far rarer than our models suggest, or something is preventing it from becoming visible across cosmic distances. This realization shifts the focus of the search, moving it away from simply looking harder and toward understanding why nothing appears at all. To explore that question, scientists needed a way to break the problem into smaller parts, not as a single mystery, but as a chain of probabilities. In 1961, that effort would take form as an equation that does not provide a clear answer, but instead reveals how much we still do not know, and how many assumptions we are forced to make. An equation that would turn the question into a framework and the mystery into something we could begin to measure. In 1961, scientists attempted something ambitious, not to find alien life directly, but to measure the chances that it exists at all. At the Green Bank Observatory in West Virginia, astronomer Frank Drake introduced a framework that would become one of the most influential tools in the search for extraterrestrial intelligence. It is known as the Drake equation. Despite its name, it is not an equation that gives a single answer. It is a way of breaking a massive question into smaller parts, each representing a step in the development of intelligent life. The idea is simple. Start with the number of stars that form in the galaxy each year, then estimate how many of those stars have planets. Of those planets, how many could support life? Of those, how many actually develop life? Then how many evolve intelligence? How many develop technology? And finally, how long such civilizations survive. Each step reduces the number. Each step adds uncertainty. In simple terms, the equation asks a chain of questions. How often does life begin? How often does it become intelligent? And how long does it last once it reaches that stage? When Drake first proposed this framework, almost every term was unknown. Scientists could only guess. But over the decades, that has started to change. We now know that stars are constantly forming in the Milky Way at a rate of about 1 to 3 per year. We know that planets are common and that most stars host planetary systems. Observations from missions like Kepler have shown that a significant fraction of stars have Earth-sized planets in regions where liquid water could exist. This means the early parts of the equation are no longer uncertain. There are plenty of places where life could begin, but the later terms remain unknown. We have only one confirmed example of life in the universe, and that is Earth. We have only one example of intelligent life, and only one example of a technological civilization. This creates a problem. We are trying to estimate universal probabilities using a single data point. The result is that the Drake equation can produce very different answers depending on the assumptions used. In some models, the galaxy should be filled with thousands of active civilizations. In others, we may be alone. Both outcomes are consistent with the equation. And that is what makes it powerful. It does not solve the mystery. It organizes it. It shows us exactly where our knowledge ends. The early steps are becoming clear. The universe has stars, planets, and the basic conditions for life in abundance. But somewhere along the chain, something reduces the number dramatically. Either life rarely begins, or intelligence rarely evolves, or civilizations do not last long enough to be detected. The equation does not tell us which of these is true, but it makes one thing clear. The silence we observe is not caused by a lack of opportunity. There has been enough time, enough stars, enough planets. Something else is responsible, and that realization leads to a more unsettling idea. What if there is a step in this chain that almost no civilization ever passes? A barrier so difficult, so unlikely, that it prevents life from spreading across the galaxy. A filter. And the most important question becomes this: is that filter behind us, or still ahead? Because the answer to that question does not just explain the silence of the universe, it may determine the future of our own civilization. What if the silence of the universe is not a mystery, but a warning that has been there all along, waiting for us to understand it? In 1998, an economist named Robin Hanson proposed an idea that would reshape how scientists think about the Fermi Paradox, and although he was not an astronomer, his reasoning addressed a gap that observational science alone could not fill. He called it the Great Filter. The concept begins with a simple but powerful observation. Between lifeless matter and a civilization capable of exploring the galaxy, there is a long chain of steps, each representing a transition from chemistry to life, from simple cells to complex organisms, from intelligence to technology, and finally from technology to interstellar expansion. For a civilization to reach the stars, every one of these steps must succeed. Yet the more steps there are, the greater the chance that one of them is extremely rare. If even one step is unlikely enough, it becomes a filter that almost no civilization can pass, reducing the number of advanced civilizations in the galaxy to near zero. In simple terms, the Great Filter is a barrier somewhere in the development of life, and it offers a possible explanation for why we do not see evidence of other civilizations. The critical question is not whether the filter exists, but where it lies in this chain of events. One possibility is that the filter is behind us, meaning that something in our past was extraordinarily rare, such as the origin of life, the emergence of complex cells, or the development of intelligence, any of which may require conditions so specific that they almost never occur. If this is correct, then humanity may be one of the very few technological civilizations in the galaxy, and the silence we observe would not be surprising, but expected. The alternative possibility is far more unsettling because it suggests that the filter is not behind us but ahead. If life forms easily and intelligence is common, then many civilizations may reach a stage similar to ours, developing technology, increasing energy use, and beginning to reshape their environments, only to encounter a barrier that prevents further progress. This barrier could take many forms, including self-destruction through advanced weapons, environmental collapse caused by unsustainable growth, or the unintended consequences of technologies that evolve faster than they can be controlled. There is no confirmed mechanism, but the pattern is consistent with what we observe, because civilizations may arise, yet fail to last long enough to spread or be detected across interstellar distances. The timescale becomes essential, because if a technological civilization survives for only a few thousand years, its signals would be brief, its expansion limited, and its presence easy to miss within a galaxy that is billions of years old. Such civilizations would appear and disappear like brief flashes, too short-lived to overlap with others, and too distant to leave a lasting trace. This transforms the Fermi Paradox into something more immediate and more personal, shifting it from a question about distant civilizations into a question about our own future. If the filter is behind us, then we are rare. But if the filter is ahead of us, then we are early. And being early may mean we are approaching the most difficult step of all. The evidence so far does not provide a clear answer, but it does narrow the possibilities, because whatever the filter is, it has been effective enough to keep the galaxy silent, and that silence leads to one final possibility that is quieter, but no less profound. What if civilizations do survive, avoid collapse and reach stability, yet choose not to expand or reveal themselves? If that is the case, then the absence we observe may not be the result of failure, but of restraint, and the silence of the universe may not be emptiness at all. It may be intention. What if the universe is not silent because it is empty, but because it is quiet by design? By the mid-2020s, after decades of searching, scientists began to seriously consider a possibility that once seemed unlikely, not because of a lack of imagination, but because it challenged a deeply human assumption, the assumption that advanced civilizations would expand. In 2025, researcher James Corp and others revisited this idea through what is sometimes called the mundanity hypothesis, which suggests that the absence of evidence may not be the result of destruction, rarity, or failure, but of choice. The reasoning begins with a simple question: why would a civilization spread across the galaxy at all? From a human perspective, expansion feels natural. Our history is filled with exploration, migration, and growth. But this behavior may not be universal. It may be a product of biology, culture, or circumstance, rather than a fundamental rule of intelligence. Interstellar travel is not just difficult, it is extraordinarily expensive in terms of energy, time, and uncertainty. The nearest star system is over 4 light-years away, and even at speeds far beyond our current capability, a journey would take decades or centuries. The energy required to accelerate a spacecraft to such speeds would rival the output of entire nations. And when it arrives, there is no guarantee of success. A distant planet may be habitable, or it may be hostile, unstable, or already lifeless. The risk is immense, and the reward uncertain. From this perspective, a highly advanced civilization might reach a different conclusion. Instead of expanding outward, it might turn inward, focusing on stability, efficiency, and long-term survival within its own system. In 2022, researchers Michael Wong and Stuart Bartlett explored how civilizations evolve over time and found that unchecked growth leads to what they called asymptotic burnout, a state where increasing complexity and resource consumption eventually become unsustainable. The alternative is what they described as a homeostatic state, where growth slows, stabilizes, and reaches balance. A civilization in this state would not be driven to expand aggressively. It would conserve energy, minimize risk, and maintain equilibrium. Such a civilization would be difficult to detect. It would not broadcast powerful signals into space. It would not construct massive structures that alter the light of its star. It would not send fleets of probes across the galaxy. It would exist quietly. This idea does not contradict the Fermi Paradox. It reframes it. The absence of signals may not mean the absence of civilizations. It may mean that advanced civilizations do not behave in ways we expect, and that our search methods are based on assumptions drawn from our own early stage of development. If this is true, then the silence is not a failure of detection, but a reflection of misunderstanding. We are listening for voices that may no longer be speaking, or perhaps never needed to. This brings the story full circle, from a single unexplained signal in 1977 to bursts of energy across the universe, to distant planets with uncertain signs of life. Every discovery has pointed toward possibility without confirmation. The universe offers hints, but not answers. And so, the question remains, unchanged since 1950. Where is everybody? The answer may lie not in the distance between stars, but in the nature of intelligence itself, in how civilizations choose to exist, and in whether we are asking the right questions at all, because the final possibility is the most subtle one, that the universe is not empty, it is simply not speaking to us in a way we yet understand.